Now I want to take a look at what the derivative of a function will tell us about that function. In particular, what it tells us about the shape and the nature of its graph. Now, you can imagine if you had a function that was sort of fluctuating and it's uphill at times, downhill at times, increasing at times, decreasing at times. If you were to look at points on that graph, let's pick a point right here and let's draw a tangent line. You notice as that graph is running uphill, that tangent line is going to have positive slope. Also notice if we move over here and pick a point, and again, do our best to draw a tangent line, notice that that tangent line is going to have a negative slope. All right, so it is seemingly, at least to me, obvious to say that the derivative of a function, which tells us its slope at a particular point, is going to tell us what we need to know as far as increasing or decreasing type behavior. So the first derivative tells us that if f prime of x is greater than 0 on some interval, then the original function f of x is increasing on that interval. All right, like it was doing right here. All right. Secondly, if f prime of x is less than 0 on an interval, then f of x is decreasing on that interval. All right, now in addition to that, before I do anything to test increasing or decreasing behavior of a particular function, something else I would like to go ahead and point out is that we've already noticed that when the derivative is 0, you can have a max or you can have a minimum value, in particular a local max or a local min. Again, notice I emphasize can have. It does not mean you have to have. So far, what we've been doing is taking those x values, plugging them in, and just doing side-by-side comparisons. But now that we can spot increasing and decreasing behavior, we can do a little bit better than that. Notice that in this drawing, you're going to have a local maximum around about that point. Also notice that at that point, you would, of course, have 0 slope. And in particular, the function went from positive to 0 to negative as you moved along its surface, which means that as a function goes from increasing to decreasing, if it passes through a slope of 0, then it will create a maximum at that location. Over here, we have a local min, and this slope is going to go from negative to positive as it passes through that slope of 0, which is why the minimum was created. That's how it got there. So that brings us to what's commonly called, in most books, the first derivative test. And it basically says that if c is a critical number of a continuous function, which means critical number, again, remember means the derivative was either 0 or undefined. In these two cases, it was 0. But anywhere where the derivative was either 0 or undefined, and the derivative changed from positive to negative at that location, a local max was created. If it changed from negative to positive, a minimum was created. So the way I like to write this up to make it just sort of as easy to follow and understand as possible is with a couple number line sketches. Let me show you what I mean. Let's say I had f of x equaling 2x cubed plus 3x squared minus 36x. The first thing I'm going to do is take the derivative. This is not a difficult one to take. F prime of x is going to be a 6x squared plus a 6x minus the 36. I'm going to take that derivative and either see where it will equal 0 or will be undefined. Well, since the derivative is a quadratic, it's never going to be undefined. So now I'm just going to leave me to just finding out when is it equal to 0. So I'll factor out the 6, factor as two binomials, and solve. All right, so what am I going to do with that solution? Well, those two numbers are critical numbers. Those are locations where the derivative is equal to 0, and that was at -3 and +2. And again, I always label my number line so I know what it is I'm testing. All right, so I will take the calculator and put the derivative, because remember, the derivative that I'm testing, put the derivative into the calculator, not the function, the derivative. And I'm going to go to a table of values. All right, and first I will check this interval right here by picking any number in that interval and putting it into my calculator, like -4. And it does not matter that I got a 36 as an answer. That's not the point. The point is, on this interval, the first derivative was positive, therefore the function was increasing. Going to the next interval and putting in a number like 0. And what I get is a negative response, which tells me the function was decreasing over that interval. Move up to the last interval, the third interval, and put in something like a 5. And I get a positive result, which means the function was increasing again. So this function literally went from increasing to decreasing at -3. That makes -3 a local max. Here it went from decreasing to increasing. That makes 2 a local minimum. All right, so again, just using the first derivative, without looking at a picture of the graph at all, I know that I have a local max located at -3, and I have a local min located at +2. All right, so let's try that test one more time. Let me find a problem where that would be, test would be suitable to use. All right, here we go. All right, let's say I had f of x equaling x squared over x minus 2 squared. First thing I need to do is take a derivative. And for this one, derivative is going to require a little bit more than just a power rule. I'm going to have to use a quotient rule. All right, so f prime of x will be equal to bottom times derivative of top minus the top times derivative of bottom, and the derivative of bottom would be a 2 times the x minus 2 reduced to the first power times the derivative of x minus 2, which of course is a 1. All right, so this is bottom, derivative of top, minus top, derivative of bottom over the bottom, squared. And since the power was already a second power, squaring it, we'll bump it up to the fourth power. And with these derivatives, let me advise you, clean them up as much as is humanly possible. So I notice I have an x minus 2 that is a GCF. I'm going to pull it out. And I also have a 2 that's a GCF. I'm going to pull it out. And I'm going to have an x that's a GCF, so I'm going to pull it out. So the 2x, x minus 2 squared, turns into just an x minus 2. And here the 2 and the x minus 2 and one of the x's is gone. All right, so again, give you a moment to look at that factorization. That looked good. All right, and the bottom is the x minus 2 to the 4th power. So with a little bit more cleanup, we have the 2 on top, we have the x on top, the x minus 2 on top, and a 2 minus, an x minus 2 minus x is just a negative 2. And multiplying, still have the x, and one of the x minus 2's will cancel, and that power will drop to a 3rd power. So that, I would hope you realize that is a much cleaner version of the derivative, definitely the form that you want to use for all the work we're going to do here on out with this function. Okay, setting this equal to 0 means setting the top equal to 0, and making this undefined means setting the bottom equal to 0. All right, the derivative is undefined at 2, and it's 0 at 0. So I will go to the calculator, and notice that I will be putting in my simplified version of the derivative. Okay, so there's what my derivative looks like once keyed into the calculator. And I'm going to draw my number line, making a note to myself that this is a first derivative number line. I'm going to mark it at 0. I'm going to mark it at 2. Okay, and then I'm going to test some numbers. I'm going to put in something like a negative 1. Oops, not there. I'll go to my table of values and put in a negative 1. And it's negative, which tells me that this function was decreasing. Put in a number in this interval, like a 1. And it's positive, which tells me it was increasing. Put in a number up here like a 3, and it's negative. It tells me decreasing again. All right? So, at this point, since the function went from decreasing to increasing at 0, I have a minimum here. And again, it's in particular, it's a local min. I have a local min because it went from decreasing, it went from going down to up. Here, it went from increasing to decreasing. It went from up to back down. So I would be tempted to say I have a maximum here. I would be tempted to say that. But if you look at your original function, you see that the function is not actually defined at 2. All right? This function has a vertical asymptote at 2 because that puts a 0 in your denominator. So this is not a max. This is a vertical asymptote. All right, max, that is a vertical asymptote. The function's not actually defined there. So for a point to be a local max or a local min, it actually has to be a point on the graph. It actually has to be defined there. So you might want to pay attention to asymptotes in advance. In hindsight, maybe that's something we should have looked at. A 2 for x at x equal 2, this thing had, as I just said, vertical asymptote. So nothing's going to happen there in the way of maxes or mins. The function's not defined there at all. Since I have a second degree polynomial on top and a second degree polynomial on the bottom, and the leading coefficients are in 1-to-1 ratio, y equal to 1, just while we're on the subject, your horizontal asymptote. Okay, this is all stuff you should have covered in pre-cal. And it just sort of flashed back to me, maybe I need to mention that. But again, I did not have a max or a min here because I had a vertical asymptote there. All right, so be on the lookout for vertical asymptotes. Horizontal asymptote is just something that's not bad to keep an eye out for, just when you're trying to figure out the nature of the graph. All right, so there that is. All right, now the next thing we need to go on to, and I think I'll keep this example as I go on. The next thing we want to talk about is what the second derivative of a function will tell you. All right, if you have a function and let's say the second derivative is greater than 0, second derivative is a positive number, then what that tells you is the function is what's called concave up. That's the terminology that is used, concave up. Concave up, basically, the easiest way to think of it means that the function will hold water. It's cupped upwards. Now, if f double prime is less than 0, the function is concave down, which means it won't hold water. It will mean more of a shed water type of shape. All right. And of course, functions that are concave up could potentially have local minimums. Functions where they are concave down, oops, I said down instead of saying concave. Where they are concave down, you might have a local max. All right, so that's something to watch out for. As a matter of fact, the second derivative test says, sort of highlight it here, you have a second derivative test, which is a second way to find local maxes and mins. If f prime of c is equal to 0, and the second derivative at that point is greater than 0, then you have a local min. And again, f double prime greater than 0 means it's that concave up shape, and that's why you can see a local min there. F prime of c is equal to 0, and f double prime of c is less than 0, again, meaning it's that concave down shape, then this point could be a local max. Okay, maxes and mins can be found using the first or second derivative test. I prefer the first, as I've just shown you, but the second is okay as well. Let me pick back up with this example that I had and show you what I'm talking about. Our original function was x squared over the x minus 2 quantity squared. Our first derivative, once simplified, turned into negative 4x over x minus 2 to the third. Let's find a second derivative. Second derivative would be bottom, derivative of top, and the times 1 is because of the derivative of the x minus the top times derivative of the bottom. The bottom means bringing down the 3. X minus 2 drops to the second power times the derivative of x minus 2, which is a 1. And it's all going to be over at the bottom, squared, which bumps that power up to the 6th power. Right? And then for some cleanup. Let's do this first. Negative 4 times the x minus 2 cubed. Two negatives make a positive. And, oops, I missed that 3 for just a second. 4 times 3 is 12. And the x. And the x minus 2 squared all over the x minus 2 to the 6th power. All right, now I'm going to factor. I'm going to pull out an x minus 2 squared. I'm going to pull out a 4 while I'm at it. And use a negative sign there, and x minus 2 to the 1st power only, plus a 3x, like so. All right, because I factored out the 4, That's where the 3 came from. And I'm over in x minus 2 to the 6th power. All right, what happens next is 2 of these, factor of the 6 of those. Power drops to the 4th power. There's a 4 out front. And this is a negative x and a 3x, which is a 2x and a 2. Okay, so now I'm going to set the top equal to 0. And I get a negative 1. So the bottom equal to 0. And I get an x equals 2. All right, now let's compare those numbers. What we had before. And we'll again notice that before at the 2, I said I had a vertical asymptote. All right, so again, since that's not in the domain of the original function, nothing's going on here. Nothing's going on there. All right. At that point, no maxes or mins, but what I would do is I would set up a number line test, just like I did before. Let me just back on the camera. F double prime of x. All right, I'm going to test that on the number line. So I will go back to the calculator, put in the derivative. So I'm going to put a 4 and a 2x plus 2 in the numerator. Divide that by an x minus, wait a minute, and those are parentheses, and x minus 2 power 4 in the denominator. And let's set up a table. All right, I'm going to take my number line and cut it at -1 and +2. All right, so testing down here below -1 using a number like a -2, I get a negative value, but it's not the negative that matters. It's the fact that this is concave down. Putting in a number like 0, positive, making it concave up. Put in a number like 3, and it's positive. That makes it concave up again. All right, now a point of inflection is defined as a point at which the function changes concavity. All right, so at -1, we will have a point of inflection, again, meaning the function changed from concave up to concave down. I'm sorry, concave down to concave up. At 2, it did not change, and 2 could not have been a point of inflection anyway because it's not in the domain of the function in the first place. All right, so I've got my concavity figured out. I have found my 1 point of inflection. Let's talk about this max and min issue. All right. At 0, I had previously said I had a local min because it went from decreasing to increasing. Also notice that 0 is in this interval. So at 0, my derivative was 0, and at 0 it was concave up. That reinforces the fact that 0 was a local min. All right. Also notice that at 2, all right, you're not in the domain. That's something you always have to be careful of. So it can't be a local max, can't be a local min, can't be a point of inflection. It's not in the domain, and it's a vertical asymptote. All right. So again, the second derivative test can also be used for finding local maxes and local mins. I very much prefer to use the second derivative just to find concavity and find points of inflection, and let the first derivative tell me about local maxes and mins, while still yet keeping a careful eye on your domain. Don't claim you have local maxes, local mins, or points of inflection at locations where you're not even in the domain of the function.